In this section, we're going to be discussing asymptotes and how we can connect all the information that we've learned to sketch the graphs of functions. So first of all, let's start by defining a horizontal asymptote. Horizontal asymptote basically describes when the end behavior, the ends of a function, flatten or become horizontal. So we're going to say that the line y equals L is a horizontal asymptote if our limit as x goes to positive infinity equals L, or the limit as x goes to negative infinity equals L. So the idea is if you look at the right side as x goes to infinity or the left side as x goes to negative infinity, if the function approaches a constant, that means you have a horizontal asymptote. All right, so how do we find horizontal asymptotes? Well, we can take the limit as x goes to infinity. So let's find the limits. I've got a list of 3 limits as x goes to infinity, and then we're going to use our answers to determine whether the function has a horizontal asymptote. So let's start with part A. Limit as x goes to infinity of 5x minus 1 over 4x squared plus 2x. If we try to just plug the infinity in, we end up getting infinity over infinity, which is indeterminate. That means we have more work to do. It's a lot like when we get that 0 over 0. And so the approach I'm going to show you is where we divide every term by the largest power of x. So looking at this problem, the largest exponent I see is that x squared. My largest power of x is x squared. So I went ahead and I divided every term, both on the top and both on the bottom, by x squared. And now we're going to try to simplify. We're going to reduce each of these 4 fractions. So the 5x over x squared, we can cancel out an x. It becomes 5 over x. And then the second term on the top is a 1 over x squared. And then on the bottom, 4x squared divided by x squared is just 4. And 2x divided by x squared reduces to a 2 over x. So I divided everything by the largest power of x. And then I'm going to simplify or reduce. And then finally, I plug that infinity in again. So on the top, we've got 5 over infinity. And to solve this, we're going to use the fact that anytime you take a finite number, like 5 or 7 or negative 3, anytime you take a finite number and you divide it by infinity, it's always going to go to 0. So when you divide by something very large, you get something small. And so that means if we divide by infinity, it should go to 0. So in the top of this fraction, we've got the 5 divided by infinity, that goes to 0, minus 1 over infinity, that also goes to 0. And then on the bottom, we've got 4 plus 2 over infinity, and the 2 over infinity goes to 0 as well. So I'm left with just 0 on the top, 4 on the bottom. 0 divided by 4 is 0. So this limit equals 0. What is that telling me in terms of asymptotes? That means y equals 0, again, because 0 was my answer, y equals 0 is a horizontal asymptote. All right, let's do another example. Let's look at the part B, which was the limit as x goes to infinity of 2x squared plus 4x over 9 minus x squared. Again, if we try to plug in the infinity, we end up getting infinity over infinity. And so we are going to use the same approach. We're going to divide everything by the largest power of x. Once again, the largest power of x is the x squared. So I'm going to go ahead and I'm going to divide the 2 terms on the top and the 2 terms on the bottom by x squared. So now I have limit x goes to infinity, 2x squared over x squared plus 4x over x squared all over 9 over x squared minus x squared over x squared. We can reduce each of these fractions. The first fraction on the top, the x squareds cancel out, and we're just left with 2. And then the 4x over x squared, we can cancel out an x, we're left with 4 over x. On the bottom, we've got a 9 over x squared, and then the x squared over x squared reduces down to a 1. So we've simplified each of these fractions, and then we're going to plug that infinity in. And anytime we have a constant, or a finite number over infinity, it goes to 0. And so we end up getting 2 plus 4 over infinity, which goes to 0. So we end up just getting 2 on the top, and then on the bottom, the 9 over infinity goes to 0, and then we've got the minus 1. So we just have a minus 1 on the bottom. 2 divided by minus 1 is negative 2. So this limit equals negative 2. Does this function have an asymptote? Yes, y equals negative 2 is our horizontal asymptote. So whatever you get for this limit is your asymptote. The only time it doesn't have a horizontal asymptote is if you end up getting a limit that doesn't exist, or a limit that equals infinity. But if your limit equals a number, that is always going to be your horizontal asymptote. All right, we had one more example, example C. This problem had the square roots in it. Its limit as x goes to infinity, square root of 9x squared plus 16, all over 2x, plus square root of x squared plus 1. We're going to use the exact same strategy. We're going to divide everything by the largest power of x. So this problem, in the numerator, the only x I see is an x squared, but that x squared is inside the square root. So in the numerator, we've got a square root of x squared, which is an x. So that's what we have in the numerator. And then in the denominator, I've got an x to the 1. And then I've got another x squared inside a square root. So we've got an x to the 1 and another square root of x squared, which is also x. So technically, my largest power of x is x to the 1, or the square root of x squared. So we're going to go through and we're going to divide everything by x to the 1. And so that's what I've done next, is I'm going to take the top, square root of 9x squared plus 16, and I'm going to divide that by x to the 1. And then I did the same thing on the bottom. I'm going to take the 2x, divide that by x, and then the square root of x squared plus 1, and divide that by x. Now, to do this division, because we have these square roots, we're going to use the fact that x is the same thing as the square root of x squared. So anytime I'm dividing those square roots by an x, I'm just going to replace that x with a square root of x squared. Okay, so I'm technically dividing the square roots by square root of x squared. That's the same thing as x, because x is positive here. We're going to positive infinity. All right, so that little trick is going to allow us to do that division inside the square root now. So in my numerator, I have square root of 9x squared over x squared plus 16 over x squared. And then on the bottom, we still have that 2x over x that's not inside a square root. And then plus square root x squared over x squared plus 1 over x squared. So basically, kind of to summarize what happened here with this kind of little trick that we did, is everything that was outside of the square root, I just divided by x. And then if I wanted to do division inside the square root, I had to divide by an x squared. And so that's basically what happened here. Now, just like in the previous problem, we're going to simplify. We're going to cancel things out. So numerator, the first term, we've got this 9x squared over x squared. The x squareds cancel, and we're just left with 9. And then the second term, 16 over x squared. And then on the bottom, 2x over x, the x's cancel. We're just left with 2. And then we've got a plus square root. X squared over x squared becomes a 1. And then we've got plus 1 over x squared. All right, so finally, now that we've simplified, we can plug our infinity in. And we're going to use that same fact that anytime we have a constant or a finite number over infinity, it's going to go to 0. And so what we're going to be left with in the top is square root of 9 plus 0, or square root of 9, or 3. And then on the bottom, we are left with a 2 plus square root of 1 plus 0, so 2 plus 1, or 3. 3 divided by 3 is 1, so my limit equals 1, and that tells me that y equals 1 is my horizontal asymptote. All right, I want to do 2 more examples that are a little bit different. So in the previous examples, we had x to a power, we had powers of x, and so our approach was divide by the largest power of x. I want to show you a couple of other limits as x goes to infinity that are a little bit different. So let's look at arctangent of x. Let's see what happens if we find the limit as x goes to infinity. So first thing I'm going to do is just plug in the infinity for x, and I want to think about, well, what is arctangent of infinity? Well, so if we're considering the function y equals arctangent of x, we can rewrite that. That's equivalent to saying tangent of y equals x. Recall that arctangent and tangent are inverse functions. They switch the x's and y's around. And so that means if we're plugging the infinity in for x, we are trying to figure out when does tangent of y equal infinity. If we replace the x with an infinity, we're trying to figure out what angle gives us a tangent of infinity. And so to do that, we are going to think about the fact that tangent is defined to be sine over cosine. So if tangent of y equals infinity, we want to know when does sine of y over cosine of y equal infinity. And when are we going to divide and end up with infinity? That's going to happen when the denominator goes to 0. So this problem is really asking us, when does that denominator, cosine of y, go to 0 or equal 0? And so that we can actually determine by thinking about our unit circle. So with arctangent, we really only have to consider the right half of the unit circle. So cosine is the x-coordinate on the unit circle. So when does the x-coordinate equal 0? Well, I guess technically that happens at 2 places, at pi over 2 and at negative pi over 2. But we want to know what angle gives us a positive infinity, so we're really only worried about that quadrant 1. Tangent is positive in quadrant 1, and so the angle that has a cosine of 0 would be pi over 2. So when our angle equals pi over 2, tangent is going to go to infinity. So that means as x goes to infinity, arctangent goes to pi over 2, and that is our answer here. And let me just write that down for you. The answer, the limit as x goes to infinity of arctan of x equals pi over 2. That's the angle that gives us a tangent of infinity. All right, let's take a look at example B. If we want to find the limit as x goes to infinity of 2e to the x minus 3 over e to the x plus 1. So let me give myself a little bit more space here. So the first thing I would try is just plug the infinity in, but if we do that, we end up getting an e to the infinity, or infinity over infinity, which is indeterminate. And so in this example, we're going to use a strategy that's really similar to what we did in the previous problems. Let's try to divide everything by e to the x and then simplify. So I'm going to take the 2e to the x divided by e to the x plus 3 divided by e to the x all over e to the x divided by e to the x plus 1 over e to the x. Then we can simplify, we can reduce, we can cancel these e to the x's out. So the numerator is now 2 plus 3 over e to the x. And then on the bottom we do some canceling and we get 1 plus 1 over e to the x. Now when we plug the infinity in, our numerator becomes 2 plus 3 over e to the infinity, and e to the infinity goes to infinity. So once again we have that finite number, the 3 over infinity, and that goes to 0. And then on the bottom something similar happens. We've got a 1 plus 1 over infinity, so 1 plus 0, and I'm just left with 2 over 1, or 2. In the second part of this video, we're going to talk about using the things we've learned both in this section and the previous section to create graphs of functions, or to do curve sketching. And so basically what we're going to do is we are going to use the first derivative to determine where the function is increasing or decreasing. And then we're going to use the second derivative to figure out where it's concave up or concave down. And then we can find the maxes, the mins, the inflection points, and put all that information together to sketch the graph. And so basically when you're creating your graph, I've summarized kind of the 4 different ways that you might be connecting the dots in this table on the screen. So if you look at the top left, you could have a function that is increasing and concave up, and I've drawn what that looks like, increasing, concave up. Bottom left, that would be increasing and concave down. And then if you take a look at the column to the right, that shows you what the graph looks like if it's decreasing and concave up, and then decreasing and concave down. So those are really the 4 options when we're creating the graph of our function. All right, so let's just dive in and look at an example. We are going to analyze the first and the second derivative to sketch the graph of the function f of x equals 3x over x squared plus 1. So the first thing we need to do is find our first derivative. This is a fraction, so I'm going to use my quotient rule. The top, the f, is the 3x. The bottom, the g, is x squared plus 1. So my f prime would be 3 and my g prime is 2x. I'm going to plug that into my quotient rule. I'm going to take f prime times g minus g prime times f all over g squared. That gives me the 3 times x plus 1 minus 2x times 3x over x squared plus 1 squared. If we do the multiplication, if we distribute the 3, we get 3x squared plus 3 minus 6x squared. Denominator is x squared plus 1 squared. I combine like terms on the top. That gives me minus 3x squared plus 3 over x squared plus 1 squared. So there's my first derivative. I'm going to analyze that first derivative to determine where's the function increasing, decreasing, and does it have any maxes or mins. So I have to find the critical points. I'm going to set this derivative equal to 0. And the only way a fraction can equal 0 is if the top equals 0. So let's set the top, minus 3x squared plus 3, equal to 0. Then we can solve for x. So I minus the 3, divide by negative 3. That gave me x squared equals 1. I take the square root, don't forget the plus or minus. So x equals plus or minus 1 are my critical numbers. Now, technically, we would want to think about also where does the bottom equal 0, but in this particular case, x squared plus 1 will never equal 0. If you try to solve that, you'll get imaginary numbers. So we really only have to worry about the positive 1 and the negative 1. And so I'm going to create a table using the number line. I'm going to put my critical numbers, negative 1 and 1, into my number line. And then I'm going to pick a test value that's smaller than negative 1. I chose negative 2. Something between negative 1 and positive 1, I chose 0. And then something that's bigger than 1, I chose 2. I'm going to take these test values and I plug them into my derivative to analyze whether that derivative is positive or negative. And so if you take negative 2 and you plug that into your first derivative, you would be computing negative 3 times negative 2 squared plus 3 all over negative 2 squared plus 1 squared. I ended up getting a negative answer. Specifically, I got this fraction, negative 9 over 25, but really the thing I need to keep track of is that that answer is negative. And then I did the same thing. I plugged in 0 into my first derivative. I got a positive. I plugged in positive 2, and I also got a negative answer. So where the first derivative is negative, the function is decreasing. Where it's positive, it's increasing. So that means this function is increasing from negative 1 to 1, so in the middle, decreasing everywhere else. Negative 1 has to be a minimum, and positive 1 has to be a maximum. I can get the y coordinates of my min and max. I can get those y values by taking both 1 and negative 1 and actually plugging that into the original function. So I took 1 and I plugged that into the 3x over x squared plus 1. That gave me 3 halves, and when I plugged negative 1 in, I got negative 3 halves. Okay, so all of this work on this screen is analyzing the first derivative. So now I know where the function is increasing, decreasing. I know that it has a max and a min. The next step is to repeat this process, but looking at the second derivative. So if my first derivative is negative 3x squared plus 3 over x squared plus 1 squared, I have to use the quotient rule again to find that second derivative. So the top is the negative 3x squared plus 3, that's my f. The g is the bottom, x squared plus 1 squared. So my f prime is negative 6x, and then I used the chain rule to find my g prime. So I brought the 2 down, 2x squared plus 1, and then I multiply by the derivative of the inside. The inside is that x squared plus 1, so that's why I had to multiply by that 2x. I'm going to plug these things into my quotient rule. So it's a little bit messy, but I'm taking my f prime times g minus g prime times f all over g squared. So I plugged everything into that quotient rule. And then I'm going to make some kind of attempt to simplify this. So let's see. Let's start with the numerator. We've got the negative 6x, x squared plus 1 squared. And then for the second term, minus, right now the only thing I'm going to do is I'm going to take the 2x and the 2 in the g prime and multiply those things together. So that's how I got the minus 4x, and then I just copied down the x squared plus 1 minus 3x squared plus 3. And then on the bottom, you can multiply the exponents. So x squared plus 1 squared squared becomes x squared plus 1 to the 4th. Now the next thing I'm going to do is I'm going to try to factor the numerator, and that's going to allow me to do some canceling. So I notice that both terms in the numerator have an x squared plus 1. I've underlined that in red for you. So both terms have an x squared plus 1. And then I can also take an x and a 2 out. I kind of underline that in purple. So I'm going to say that my GCF is 2x, x squared plus 1. And so I'm going to pull that out front. And then the first term, we're just left with the negative 3. And if we took one of those x squared plus 1's out, we just have one of them left. So first term, I'm left with a negative 3 x squared plus 1. Second term, when we take the 2x out of the 4x, we're left with a 2. So that's why I wrote down minus 2. We take the x squared plus 1 out, we're just left with the minus 3x squared plus 3. And then I haven't done anything to the bottom, it's still an x squared plus 1 to the 4th. So now the next thing I'm going to do is cancel an x squared plus 1 out of the top and the bottom. And so on the top, I'm just left with the 2x. And then inside those brackets, I now have a minus 3x squared minus 3 plus 6x squared minus 6. So I did do some distributing inside the brackets. And then if I cancel an x squared plus 1 out of the bottom, we used to have 4, now we've got 3 left over. So I'm left with x squared plus 1 to the 3rd. Okay, finally, inside those brackets, I'm going to combine like terms, and so that's how I end up with this second derivative that is 2x, 3x squared minus 9, over x squared plus 1 to the 3rd. All right, so finally we have our second derivative. And now we're ready to analyze it. We're going to set it equal to 0, and then we're going to create a number line for the second derivative. The only way a fraction can equal 0 is if the top equals 0. So I'm going to set the top equal to 0. So 2x, 3x squared minus 9 equals 0. And technically we do have to think about, does the bottom equal 0? But once again, the bottom will never equal 0. X squared plus 1 will not equal 0, so we don't have to worry about that. Okay, so let's see, 2x equals 0, divide by 2, so when x equals 0, and 3x squared minus 9 equals 0, I added the 9, I divided by 3, that's how I got x squared equals 3. I take the square root, don't forget the plus or minus, so x equals plus or minus root 3. So I have 3 numbers that I have to put on my number line. I have to put negative root 3, 0, and root 3. I'm going to pick test values in between each of those regions. And so feel free to punch that root 3 into your calculator, see what it is. I think it's about 1.7. So that means if you're picking something smaller than negative root 3, negative 2 will work. And then between negative root 3 and 0, I picked negative 1. Between 0 and root 3, I pick 1. Bigger than root 3, I pick 2. I'm going to take these test values, and I'm now going to plug them into my second derivative. So I took negative 2, and I put that into my second derivative right here. My calculator told me that was negative 0.096. And so the thing I'm going to write down in my table is the negative. The important thing is I got a negative when I plugged negative 2 in. I'm going to do the same for each of my test values. And if I plug negative 1 into my second derivative, I get a positive number. If I plug positive 1 in, I get a negative. If I plug positive 2 in, I get a positive. So the negatives tell me the function is concave down, and the positives tell me the function is concave up. So this graph changes from concave down to concave up to concave down to concave up. The places where it changes concavity, so that would be the negative root 3, the 0, and the root 3, are all going to be inflection points. So I actually have 3 inflection points, and I got the y values. Let me fix that real quick. Got the y values of each inflection point by taking those x values and plugging them into the original function. So if x is negative root 3, my y value is negative 3 root 3 over 4. If x is 0, my y value is 0. And if x is positive root 3, my y value is 3 root 3 over 4. Okay, so finally, now that we have analyzed our first and second derivative, we're going to put all this information in together and create a graph. And so I've just copied down my min, my max, and my 3 inflection points. And I did convert all of those numbers into decimals to make it a little bit easier to plot. So my min is negative 1, negative 1.5. That should match with what we had a couple slides earlier. My max is 1.5. And I have 3 inflection points, negative 1.7, negative 1.3, 0, 0, and then positive 1.7, 1.3. So those are just the decimal versions of those 3 inflection points on the previous slide. So to create my graph, the first thing I'm going to do is I'm going to plot those 5 points that I have listed on the screen, my min, my max, and my 3 inflection points. And so I've done that in blue. I've just plotted a point for each of those ordered pairs. And then the idea is we're going to connect the dots using the information from our number lines. And so I like to actually take my number line and copy it down directly underneath that graph. So I've just taken my first derivative number line, and I've copied, I make the numbers line up with my x-axis. And so what we had found out earlier was to the left of negative 1, the first derivative is negative, and then from negative 1 to 1 it's positive, and then bigger than 1, it's negative again. And then I also took my second derivative number line and I put that down there as well, showing that it goes from negative to positive to negative to positive. And then finally, I am going to really connect the dots using the information in these number lines. And so I'm going to work from left to right. And so if you look at the leftmost, side of the graph, the left edge of my number lines, my first derivative is negative and so is my second derivative. That tells me I should draw something that is decreasing and concave down. And so that's what I've done, decreasing, concave down. To connect to the next dot, again, if you look at the number lines underneath, our first derivative is still negative, so still decreasing, but our second derivative is positive, so it's going to flip to concave up. And so I'm going to draw something that's now decreasing and concave up. Once you get to x equal negative 1, it changes to increasing. And so now it's going to be increasing but concave up. When you get to x equals 0, it's still increasing, but it's going to flip to concave down. So increasing, concave down. Now I'm at x equal 1. At x equal 1, it's still concave down, but now it's going to be decreasing. So decreasing, concave down. And then when you get to that x equal root 3, that's your last inflection point, it's going to flip to concave up. So decreasing and concave up. And so there's my final answer. That's a really nice graph that shows all of the important features of this particular function. All right, that's it for this video. Please let me know if you have any questions.